Hi guys, I'm Catherine. I'm a stay-at-home mom with an interest in astrophysics, and I brought along my husband Paul, who's a software engineer, and I'm going to share with you what I see and teach him a little bit about this new image that we have from the James Webb Space Telescope.
All right, I'm excited. Hello, world. This is Paul. All right, what are we going to learn today, baby?
So, let's start off with the basics. So, how much do you know about astronomy?
Everything you've taught me over the last 8 years.
Okay, cool. So, what we're looking at here is, first of all, we see a lot of stars in our own galaxy. You know what our galaxy is?
The Milky Way, but we're not looking at that, right?
We're looking through it. So, in order
Yeah.
to see the background, we have to look through the stars that are close to us. So, in this image, you can see anything that has a starburst pattern is actually something in the Milky Way. So, we've got a couple of stars. They're pretty close to us. You see a bunch up in the top. They're like 1,000 light years away-ish.
Yeah, it seems, why is that pattern typically 3, 6, or 8?
Yeah, it's actually just an artifact of the mirror configuration inside the Space Telescope itself. So when you look at the Hubble images, you'll see like a 4-point pattern, but the 6 or 8 star pattern is going to be kind of a unique signature of the James Webb Space Telescope.
Very cool. Wow,
So,
the galaxies are pretty stark.
oh my goodness, yeah, every single dot here that's not one of those stars in our own galaxy is a whole galaxy of its own that has like 100 billion stars in each one. Every little dot here is not a star, it's a galaxy. So can you like imagine you're looking out at the night sky? Like how much of the sky do you think this is?
Wow, that's a good point. So yeah, that I was going to ask, is this the sort of looking out of the night out from one point on Earth in one direction?
Yeah, this is looking out at the sky from a point on Earth in one direction. At first I thought it took up like maybe a hand's sized square on the sky, but I was way off. This is actually just a dot of sand. Like if you took a dot of sand and held it up at arm's length, that little dot, that's all of the sky that we're looking at.
Wow. Now, the Earth is rotating and revolving. So isn't the portion of the universe that it sees different? The portion that the telescope sees, isn't that not different?
Well, I mean, first of all, the telescope's in space.
Right. Is it orbiting the Earth?
I think it's like way out there.
Okay.
So it can look pretty much anywhere that it wants, but it shouldn't look towards the sun because it's too bright and it would heat up the instruments. It's got to stay on like the cold side of the telescope. So it's got to look at objects. It can't look at Mercury and Venus. It has to look at Mars, Jupiter, and outwards from there. And it can look at almost in any direction that it wants to. This one is in the southern hemisphere, so we couldn't actually see it from where we're living now. But it's just one little dot of the sky. And, you know, even these stars that you see here, they're not actually stars that we can see with our eyes. Like these are so tiny and dim. They're like 3,000 times dimmer than anything that we could see in the sky. So actually this whole image is just a black dot, any black dot in the sky.
Wow. So the light from all of these, not only galaxies, but stars, wouldn't even be a faint, dim sort of blur in the sky.
No, not perceptible at all to our eyes.
Wow.
And every single dot that we see out there that looks black is just teeming with galaxies like this.
That is crazy. Unreal.
So,
or like the kids say, no cap.
So the next closest thing other than these stars, which are about 1,000 light years, you know that like the light from this star actually left the star 1,000 years ago. We're only seeing it as it looked 1,000 years ago. We're not actually seeing how it looks today.
Wow. So and for the when you're looking at the galaxies, that's even farther back in time then.
Yeah, these smudgy galaxies or elliptical galaxies, they're about 4 billion light years away, and they're all close to one another. So most of the time when you see two galaxies in this picture, like these two, they're not actually close to one another in reality. They just appear to be close to one another. One of them is close and one of them is much further. But these white elliptical galaxies are all quite closer, gravitationally related to one another, and these ones as well. They're in one supermassive galaxy cluster that's about 4 billion light years away. So the light from those galaxies left there, and we're only seeing what they looked like 4 billion years ago.
Wow. So there's no way to look at space without also looking back into time.
Yeah.
Wow. So now what are these lens-like artifacts?
Yeah, well, these galaxies are so massive. There's so much mass in this cluster that according to Einstein's theory of general relativity, this actually bends the fabric of space and time.
Holy crap.
It's like you take a bowling ball and you stick it on a rubber sheet and it'll cause the rubber sheet to bend. Except for you have to imagine, I mean, that's only an analogy because a rubber sheet is 2D. You have to imagine that that bending is actually happening to three-dimensional space and time. The whole fabric of space-time is bending because of this supermassive galaxy.
Wow.
So that means that any light that's traveling close to that galaxy can't just go straight through the galaxy. It has to travel along the shortest path of space-time, which means it'll have to curve around the galaxy. Let me see if I can show you a picture of what that looks like. So we have this large galaxy cluster that's actually bending the fabric of space-time so that any light that's coming from behind it can't just come straight towards our eyes. It has to take this bent path. That's the shortest distance. Light will always travel the shortest distance. And if the space is curved, then the light will also curve. So it'll appear to our eyes like this star is way over here, or the galaxy is over here, but in fact, the galaxy is behind this supermass.
So because space-time is curved, oh yeah, this is a much better picture.
Yeah, so this yellow cluster is bending space and time. This galaxy is behind it, but the light is going to travel along the shortest path, which is a curve. And sometimes it'll have to go in two different directions. And what we're actually going to see is when we look, we're going to see one image of the galaxy on this side, and we're going to see one image of the galaxy on that side, all bent as if it's magnified and distorted by some kind of lens. So you'll see, like, in this case, they have 3 images, all distorted and bent, of this galaxy in the background.
So stretched out, it seems, right?
Yeah. And time also gets bent by this mass.
Wow.
So if you're close to some super massive object, then time actually moves slower as well.
Yeah, that's like that movie.
Yeah.
What was that? Gravity?
I think so.
Yeah.
Okay, let's see. So this is the supermass that's doing the bending. And then the light that is coming from galaxies behind it that's being bent is all of these warps and curved shapes. So these curved shapes are galaxies that are way behind this one, but the light is not able to come straight to our eyes. It's being warped and distorted as it comes to our eyes.
This is mind-blowing. So if one were to imagine an abstract straight line from here to there, like a Platonic straight line, it would go through the supermassive galaxy. But a concrete straight line would actually go around it because space-time is curved.
Exactly. So a straight line from us to the end of the universe actually will go curved around this supermassive.
So that means Plato's ideal forms where he's just being goofy and high. Because it ain't happening in Einstein's world.
So this is another one of those galaxies that's doing lensing. So this one is a huge mass. You can see this kind of circle, a whole bunch of arcs around here. This one is also acting like a lens, and you can see a circle of arcs that are being bent around that one as well.
Yeah, yeah.
So there's different centers to this mass. Let me zoom in on one of these galaxies that's being bent. I just love this one over here. So take a look at this galaxy. The light is being distorted and stretched because of this mass. Now, it looks like this could have been possibly two different galaxies. You see these two bright centers?
Yeah.
But actually now we know that this is one single galaxy, and we're just seeing a double image of it.
Wow.
Let me show you how we know for sure. Do you see this kind of like faint blue dot over here?
Whoa, yeah.
And there's a mirror image of that faint blue dot on this side.
Whoa.
Okay, you can see this kind of like bright starburst. Could even be a nova or a bright star birth region.
Yes.
And on this side.
Yeah.
And then you see the galactic center.
Oh, yes.
And the mirror image. You can kind of see this little bit that's popping out the end.
Oh, yes.
And this little bit popping out this end. So this is exactly mirror imaged because of this lens distortion.
Wow.
And then all of these little streaks, they're all
and what's even crazier is that this is a distorted image of a reality that was true much longer before the distorting galaxy in the foreground.
Yeah, that's kind of mind-blowing.
Yeah.
Because this galaxy is like, who knows, maybe, I don't know exactly the redshift, but it's about 10 billion years.
And probably, so do galaxies die like stars die? And
oh yeah, totally. They eventually burn through all of their hydrogen, helium.
Wow. So by the time we see these galaxies in this distorted form, they likely do not exist in this form.
Yes, guaranteed. Yeah.
That's heady stuff.
Okay, let me show you. I love this one too. This one over here is just fantastic. So this is not, a galaxy is not supposed to look like this sausage shape. It's totally being bent by this supermassive foreground galaxy. This is way behind this galaxy, and the light is just being distorted. And I'm pretty sure, I would have to check the spectrum, but I'm pretty sure that we're also seeing a faint image of this one, a second image, down a little bit lower. Let's see if I can get them both in one frame. Do you see that little smudge?
Oh, yes, yes.
So that's just a little bit of the distorted light from this orange galaxy up there.
This is almost like the effect of the diamond effect that comes in a solar eclipse, where light seems to bend over the horizon of the moon. Yeah.
Yeah, in fact, it was a solar eclipse that the Einstein's theory of general relativity was first confirmed when they saw two copies of one star on both sides of the solar eclipse that were coming towards the Earth. That was back in like early 1900s that they first confirmed that. So what else can I show you in this image? I just love these beautiful spiral galaxies. We're seeing such high resolution that we've never seen before. You can see clearly these dark dust lanes and the spiral arms.
Since the amount of light reaching us from all of this is so faint, how did they get the exposure required for this sort of imagery?
Yeah, the telescope has much more sensitive cameras this time around. So Hubble also took a picture of the same field, but it took, I think it was just 12 hours to take this picture by Webb, but it took 10 days for Hubble to get less resolution and less light coming through.
So one would imagine that, given that we're looking billions of years into the past, there's a lot of background radiation that should also reach the telescope.
Yeah. And we have to be looking at the right spectrum. So the James Webb Space Telescope is looking mostly at the infrared part of the spectrum. It's really interesting because a lot of these galaxies, especially these very, very faint and far away ones, these tiny little smudges that you see, these little dots, they're some of the oldest galaxies at the very beginning of galaxy formation in the universe. So they think the universe is about 13.7 billion light years old, or years old. So then these galaxies would be about 13 billion years away. And you know that the way that the universe is expanding, everything is redshifted.
Yeah, so the older they are, the farther they are now from us.
And they're also moving away from us faster.
Yeah.
And the faster they're moving away from us, the more the light from them is redshifted.
Right.
Just like when you hear ambulance.
So you can filter out a lot of the background radiation away from the older ones to get more of a contrast with things that are closer, it seems.
And interestingly, these galaxies, these really red ones, they have been redshifted so much that they're not even visible anymore.
Wow.
They've been redshifted out of the visible spectrum and into the infrared. So that's why it really, the Hubble Space Telescope's only looking at things in the optical spectrum. But in order to see these really, really, really distant galaxies, you need to look at the infrared because the redshift has been so strong that they're no longer in the optical part of the spectrum.
And they will never be visible.
They will never be visible.
That's crazy. So there's increasingly portions of the universe that become forever invisible to any other portion of the universe.
Exactly. Now let me show you the oldest object in this picture. Right in here, so the things that look red in this picture are actually far away. They've chosen, these colors are not the actual colors that you see with your eyes. They just chose these colors, and they chose the red colors to be far away objects. So you see this little red dot?
Yes.
So that galaxy is 13.1 billion light years away.
Oh my goodness.
And considering that the universe only began 13.7 billion years ago, this is like 500 million years into the universe. So the James Webb Telescope doesn't only take in the light, but it also is able to analyze the emission spectrum from all these different galaxies. So it can see the gas composition of these ancient galaxies, and they can see that there's hydrogen and oxygen inside of that galaxy that is the very, very beginning of the creation of galaxies.
Wow. Now, is the universe expanding at the speed of light, or?
I would have to look that one up. I'm not sure exactly what the latest rate of expansion is for the universe.
Something else interesting is, let's say it's at or even greater than the speed of light. I'm not sure if that's possible.
No, then we wouldn't see.
Yeah, so what that would mean is that all the information of all of history, of the entire cosmos, is not lost in the sense that it's traveling somewhere. So, for example, evidence of dinosaurs or even prehistoric aspects of the Earth, the imagery from that time has now left the Earth and is now traveling to distant worlds. And hypothetically, if there were intelligent species in distant worlds, they would get a record of life in the tens of millions or hundreds of millions of years ago on Earth.
Right. They would just get a snapshot of what the Earth was like hundreds of millions of years ago.
Isn't that beautiful?
Amazing.
And this is true of every point of the universe. So the entire history of almost in fact, of every point in the universe is available to some other point in the universe.
Yes.
For perpetuity, and will always be the case.
Mind-blowing.
Yeah.
So if you have any questions or comments, just throw it in the comment section and see if we can answer them. Enjoy all these images.